All right, great. What's up, y'all? How's it going? I feel like we're looking a little light. Is it like midterms or something? Is something going on? It's week 5. Today, we are going to talk about importing, exporting, and cleaning data, or otherwise data custodian work. Before we get started with that, do we have any questions for me? Wow, okay. Let's get started. So today's theme is data custodian work. These are issues around getting data in and out of R and making it analytically ready for us to run analyses. This will include things like working directories and projects, importing and exporting data using the reader and the Haven package, cleaning and reshaping data using the tidier package, dates and times using Lubridate, controlling factor variables with forecasts. So it's kind of a lot to cover, but we're going to do it. First things first, directories. You may recall that the working directory is where R will look for and save things by default. You can find out what it is using the function getWD. On my computer, when I knitted these slides, it happened to be C, users, GreeHog, OneDrive, documents, the place where the website is, the place where the class section of the website is, the lectures folder, and then week 5. I find with good project management, you virtually never have to use getWD. And we'll get into a little bit about why that is as we move on today. You can change your working directory. You can use the setWD function and specify a path to your new working directory. Some suggestions about your working directory. Markdown files use their current directory as the working directory. So just put everything you need in there. You'll find that if you go to the slides on my GitHub, that's exactly how I've set everything up. Each week is a markdown, and in that folder are all of the pictures that I'm going to use in the slides that week. All of the little data sets that I might use for an example are all in the same folders next to my markdown. I highly advise against using setWD for your markdown and instead just putting your markdown where you need the other things for. For larger projects, that is things that have more than one script, things that have many data sets. Instead of setting a working directory, it is usually better to use RStudio projects to manage working directories. For Windows users, if you copy a path from the Explorer, make sure to change / to / for the file paths. R was written in a way that cares about slashes. Windows kind of wasn't. And it is just way more work than it's worth to forget that this exists. If you need to set a working directory, put setWD at the start of your file so that someone using another computer knows they need to modify it. I'm talking about right after your name. Before you load in data, before you do packages, make the reader know that they would need to change the working directory. Better yet, set up your files in such a way that they don't have to think about that. But if you do, make it immediate. On projects in RStudio, a better way to deal with working directories is RStudio's project feature. In the top right dropdown, this has a lot of advantages. I'm going to show you where it is right quick. It's here. Top right drop down. You can make a new project right there. This has a lot of advantages. So it sets your working directory to be the project directory. So you can save that project in a folder, and now that will become your working directory for all the R scripts that are open in that project. It remembers objects in your workspace and your command history the next time you reopen that project. So you could, and although I advise against this, you could leave your objects in your environment and close the project. And then when you open it back up, they'll still be there in your environment. It reduces the risk of intermingling different work using the same variable names by using separate RStudio instances for each project. One thing I've noticed, and I'm not going to point fingers, but some folks have come to me with questions about why something is not working in their homework, for instance. And the reason is that they have all the homeworks they've ever done open. And so their environment is just full of things that are from other projects, other times, your math homework. Question?
I haven't done that specifically, but I noticed that, and I'm in all of my data. It's all there, all of the assignments. How do I do that?
Yes. What you're going to want to do, and I find this to be best practice, is you want to go to Global Options, and here you want to uncheck Restore R.data or .r data into Workspace on startup, and say Never here for saving your .r data on exit. And what this does is it makes sure you have an empty environment when you show back up. You should also know that that's going to be what you're specifying here. So if you, I don't know, have some really strong feelings about one particular thing in your environment, maybe don't do that. But also know that I judge you silently. One of the strengths of R Markdown scripts and the way that social scientists would want to use R is that it should just run when I pick it up, right? Like when I read a journal article, I like when I can pull up their R script and it just runs. I don't have to do any other setup. And so it should be when you are doing your own projects. Okay. Our projects are really easy to integrate with version control systems. So things like Git. It's really straightforward how it saves all of the things in your project at the same time and allows for really easy backtracking in your version control. Yes.
Along with not knowing that your browser shouldn't contain everything you ever did, I don't know what the word Git or GitHub is all the time.
Okay. GitHub is a management system that allows for iterative sharing of code and other text.
Okay.
And so what happens is, like, for instance, with this class, if you go to my GitHub, you will find that it'll say half an hour ago, I fixed a typo in this slide. And you can also check that an hour before that, I had changed one of the pictures. And you can also find, and so it saves things over and remembers the things that happened prior. And so sometimes you do something in a project and it ruins the whole thing, and you can just go back to the old one. And GitHub is one type of way that you can deal with version control that is called Git.
And it's open source.
It is open source, and GitHub is free, whereas GitLab is not.
Okay. And what's Git?
I'm not sure. I assume that's the name of the format of version control, but I don't know if that's exactly true, so I didn't want to mislead you.
Oh, so when you said Git up there, you're meaning GitHub. Git integrated version control systems example of Git.
an example of a version control system is Git, but I don't know any other ones.
Is Git the same as GitHub?
Git is the engine that makes GitHub work.
Okay. Yeah,
Of course.
sorry.
You're good. I usually make each RStudio project its own GitHub repository. My GitHub is very boring in that most of my Git things are private. So if you go, you'll only see like 2 folders up there. But each one of those folders is their own R project. If you're interested in advanced project management, email me after class for more resources. This will be things like the package here, or RR Tools by Ben Marwick, who's just on the other side of campus. So one of the things that helps make our projects great and our markdowns really awesome is relative paths. So once you've set the working directory, or you're in an RStudio project, what have you, you can refer to folders and files within the working directory using relative paths. So let's say I want to make a ggplot. I say library ggplot. This is going to be a plot using the cars data set, and I want to save it using ggsave. I can specify a folder that's already in my working directory without having to remember that c./my name documents yada yada yada. I can just specify relative to where my document is. Also, since I get this question a lot, let's say I want to get to a folder that's above the one that my project is nested in. This happens from time to time. An example of how you would do that would be, so like this would be if my R markdown's in the same folder where the graphics folder is. Let's say I want to get to one for which my markdown is contained. You would do .. and that's how you get to things that are in the folder that you're nested in. This is a lot like command line if you're used to doing things in Git with the command line. So the above would save an image called carsplot.png inside an existing folder called graphics within my working directory. Relative paths are nice because all locations of loaded and saved files can be changed just by altering the working directory. It's also great for when I want to hand off a, I don't know, a flash drive with a markdown inside of it. As long as that graphics folder is still there, somebody else doesn't have to have my machine in order to get all of the same things in the same folders. Oh, that basically says what I said. An example from this very slide deck is this is the code that I use to put this screenshot in this slide. And IMG right here is this IMG folder that is in my week 5 lecture. And that's where this picture is housed. Okay, do we have any questions about relative paths, working directories, R projects, that kind of thing before we move on to importing and exporting data? Cool. Question.
Going back to the very beginning, you said you wouldn't recommend doing set WD, but you would recommend doing just straight in a new project.
Yes, I wouldn't recommend using setwd because you could use an R project or an R markdown to have things saved where that document is, and then it's portable so that you can hand it off to somebody else, and it's relative to the paths in the folder. So you can just give someone else the folder, you know.
So when you just start a new project and you start a new markdown and everything will just be where that done.
Yes. I want to direct your attention to one neat thing about R being open source and lots of people having it, is if you're working with a popular data source, just try Googling it to see if it has a devoted R package already on the CRAN or on GitHub. And a caveat there is that there are packages that you cannot find on the CRAN and that they're not super vetted by R people that do exist on people's GitHubs. These are often things that are incredibly niche, like some small data set that only somebody in your field is into, or some particular type of calculation that's unique to your discipline, are often in these GitHub only repositories. But some examples of data sources that you could get from an R package, there is the World Development Indicators from the World Bank. The WHO has its own API that is wrapped for an R package so that you can query things from the API without having to understand how APIs work necessarily. There's a similar thing for this called Tidy Census, which is really great. I highly recommend Tidy Census. And part of the reason I highly recommend Tidy Census is the column names and folders come back really nice and neat. There's also QuantMod, which is like historic finance data. So if you, I don't know, day trade options, I guess you could do that. Besides a package, the easiest way to work with external data is for it to be stored in a delimited text file. These will be things like comma separated value files, like CSVs, or tab separated values. Here's an example of CSV data. You'll note that the first line is going to describe what our column names are. This is the typical setup of a CSV. And things are separated by commas. And this is how we denote columns. So here we have the date and the visitor and how many points they scored and home and how many points they scored and something that doesn't have a column name and the notes. And then we have the last 5 WNBA games that happened. And you'll see that this is a date. Some things come back as characters, so they're in quotes. Some things are numeric. Often, when you see something like this, you can just immediately recognize that this is a CSV. TSVs, on the other hand, would have tabs where all of these things are. Sometimes there's other kinds of delimiting, like a lowercase a. I've seen that, which is just horrifying if you really think about it. Often I only work in CSVs. You might recall if you've ever opened a CSV in Excel that it will say, hey, you might be losing data. The reason that it's saying that is because CSVs and Excel don't really like to format with each other. And that like all the things that Excel could do, it's not really trying to do that with a CSV. It's not like literally deleting your data. At least not anymore. It used to be the case maybe in 2007, like Windows Vista era Excel, that it only had so many rows. I don't know if that's still true. In the tidyverse, we have the reader package. R has a variety of built-in functions for importing data stored in text files. These are things like read.table and read.csv. And those are going to be like our base R reading in data functions. I recommend using the versions in the reader package, read underscore CSV and underscore TSV and underscore DLIM for a few of the features that it provides. The first of which is that it's faster. It loads way faster. We'll be getting into one of the reasons it does that in a couple slides. It has better defaults. It depends on the version of R that you have, on whether or not read.table will, for instance, automatically convert character data to factors. Reader is a little bit smarter about dates and times in that it does normally have an educated guess on whether or not you've provided it a date. It has this handy function problems you can run if there are errors, and it will yell at you when there are. And it also provides a loading bar if you have really large files. I also want to plug Vroom. Vroom is way, way, way faster. I only recommend using Vroom if you have like gigabytes of data. Otherwise, you should be fine with read_CSV. An example using the reader package. Let's import some data about song ranks on the Billboard Hot 100 in the year 2000. Also in the year 2000, the Braves were reigning world champions. So I'm hoping we can bring it home again. So you'll note when you use read_CSV, it will provide back this thing that looks like an error, but it's not. It's trying to give you useful information. This useful information can be read like this. So it's telling you column specification. And what it means is, okay, we have some columns. And the default thing that it will say a column is a double, a character type double. We also got this artist column that it's loaded. It has already considered this a character. A track column, also a character. We have the time column, which it has correctly guessed is a time. This is going to be like the length of time in the song. This is going to be the date entered, the date it entered the Billboard charts. And it has correctly guessed that it is a date. But you'll also notice that for weeks 66 through 76, all of these are logical. Now that might not be wrong. We don't have a especially good reason to think that it is right now. But typically it'll assign something logical if it doesn't quite know. And the reason that is because logical is the smallest amount of bytes saved on your computer because it's just true or false and not some other kind of data type. So often when I see a lot of things that say logical like this, and I don't anticipate that, it's worth me reading into and trying to figure out what's going on there. Another thing to note is that R is connected to the internet when you are asking it to do things. So this is just reading straight from a website. It's taking the CSV straight from the internet and putting it in your R instance. I don't know, computers are cool. So let's look at the data types for those last few columns. Note here, I've also subset this data set that I loaded in by not specifying the rows and saying the 65th column and then to the whatever the most amount of columns is in this data set. And what we see are a bunch of missing values. These are all NAs. So what went wrong? Reader uses the values in the first 1,000 rows to guess the type of column that it is for the whole length of the column. So it will guess whether or not it's an integer or logical or numeric or character. And since there are not many songs in the data that charted for, 60+ weeks, and none in the first 1,000 rows that charted for the first 66 weeks, it just said it was illogical. Part of the reason that reader is faster is because it does this, and it's normally okay. There's very few times are you in a situation where at the top of your data set, there's so much missingness that all of the rows below 1,000 are somehow very different. Since it encountered no values, reader assumed that the week 66 through week 76 columns were character, to be sure that nothing would be lost. Use the call types argument to fix this. And you can manually specify what you know a column to be, even if it's past the 1,000 rows. So the way that I've done this is I pasted a string where different letters mean the different kinds of column types. This is something you can look up if you're interested in doing it this way. You don't necessarily have to, but I wanted to expose you to this as an option. So here I means integer, C means character, and D means date. And I've repeated for integer 76 times for all of our week rows, and pasted this to the first 5 columns that we've already know that they was able to read correctly. I'll actually run this so you can see what it looks like. I guess I don't have to. You just apply it a string where each element is, or each letter denotes the kind of column that it should expect. And then you supply it to the read underscore CSV argument. And oops. You'll see now that these bottom rows are integer type instead of type logical. Some alternate solutions to this same issue on dealing with the first 1,000 rows, maybe not providing the information that will make sense for the column, is you can have it read more of the rows. So maybe the first 5,000, in hopes that it will catch the information that is inside. Note that this will like lengthen the amount of time it takes to read the document. You could also just use the read.csv function, but note that it is slower for sure and is a bit dumber. It's not going to know necessarily that things are dates. Another alternative would be using the Vroom package, a package for high-speed reading of text data like .csv files. One advantage of Vroom is you can give it a vector of file names, and it will read all of the files and then combine them into a single data frame. That's like a lot of power, and it reads it really, really quickly. But Vroom also has less error checking than Reader. So it's best to use files that you already know what all of the columns are going to be like and already know what to expect before you start just, binding rows on many gigs of data. Do we have any questions there about reading in data, these solutions here? Cool. A bit about spreadsheets. I know that in week 2, maybe I said death to them, but it's important that we cover the material still. For Excel files, that is .xls, .xlsx, I recommend using the read Excel package and the write Excel function. You can also call straight to Google Docs spreadsheets using the Google Sheets 4 package. You can load things straight from Google Sheets and send things back to Google Sheets. I haven't had a ton of use for doing so, but I do think it's neat. Note, you won't be able to keep text formatting or color or comments or merge cells. So if these mean something to you in your data, first, shame. But second, you'll need to get creative as an R user who's trying to deal with these sort of human legible things that come with a lot of Excel documents. Let's say an Excel spreadsheet is giving you grief because it has a lot of merged cells in it. The simplest thing is to just open that up and then export it to a CSV and then import it into R. I get a lot of mileage out of doing that. Be sure to compare everything carefully to make sure it works, because sometimes, you know, the merged cell will become its own NA and it'll be different depending on where you are in the column. But, you know, we're learning about the skills that you can use to deal with that today. If you need to programmatically work with non-tabular Excel sheets, particularly if you need to retain the meaningful formatting like highlighting and bold and what have you, you can look to these very powerful but very complex packages that are a bit outside the scope of this class, but these are them: Unpivoter and TidyXL. Writing delimited files. So let's say we want to get data out of R and into a delimited file. It's very similar to getting it into R. You say write CSV, your data frame, and then specify the path. This saves the data that we pulled off of the web in a file called billboarddata.csv and will be saved to your working directory. Exporting to a CSV drops our metadata, such as whether a variable is a character or a factor. You can save objects like data frames and lists, etc., in R formats to preserve this. Let's say you're one of these people that's really into thinking about data frames as lists and like to save whole data frames into cells of your data frame. It's not going to want to export to a CSV. You're going to want to do this instead. You can save things as a .rds format. This is used for single objects. And note, it doesn't save the original object name. So if you want to save it, you'll say write RDS, the old object name, and specify the path. And then when you want to load it back on, you need to assign it to an object. So say new object name and assign it read RDS, the path to that document. You can also save your multiple files using the .rdata or .rda formats. This is where you want to, if you want to preserve the original object names. So you could use save and then some bunch of objects, object 1, object 2, etc., and specify a file path. And then when you load it, note you don't have to assign it to anything. It will just load all those objects back into your environment with the original object names that you used when you saved them. I pretty much always just save to .rdata. That's just a personal preference. I don't think that there's really strong reasons to use one or the other when it comes to these. Dput. For asking for help, it's useful to prepare a snippet of your data with dput. So let's see how dput works here. Let's say we say dput the first 8 rows of the cars data set. It will return this bunch of code here, which you can then copy and assign to an object in R. This is really great for, 6 months from now, 2 years from now, when you're going to email me about a specific R problem that you have, and you're saying these columns aren't working together, you can just send me a dput, and it will allow me to work with some of the data without having to have your whole data set. This is really nice. Dputs you'll often find are also on Stack Overflow answers. There is a tidyverse version of dput called a reprex, which I believe stands for reproducible example. For most purposes, dput is fine. There isn't a lot of strong reason to use reprex necessarily. On reading in data from other software. So let's say you're working with Stata or SPSS users on some sort of joint project. You can use a package to bring in their saved files. The Haven package opens up Stata files in SPSS and SAS and is part of the tidyverse family. Haven also retains a lot of the metadata that comes from Stata. I can't speak to how well it does with SPSS. There's also the foreign package, which is like the base R read things in package. And it only works for Stata up to version 13, I think. And I believe we're on 14 now. So just bear that in mind. For less common formats, you're going to want to Google it. If they aren't things that are like a CSV or an Excel or a Stata file, there is surely somebody who's encountered the problem before. As I've said before, I've yet to encounter a data format without an R package to handle it, or at least some incredibly clever hack. Let's say you encounter a mysterious file extension like the .dat. I don't know if you all have encountered this mysterious file before, but it's really difficult to deal with because it's kind of anything under the hood. So I would recommend try opening it with a good text editor first. This will be something like Atom or Sublime, or maybe Notepad++. Don't open it up in base Notepad. It's not going to be happy with you. There's a good chance that it's actually just a raw text file with some sort of strange delimiter, like a lowercase a, or some sort of fixed format that R can handle once you've figured out sort of what's going on under the hood. Okay, that was reading in data. Do you have any questions about importing, exporting data before we move on to tidying data? Cool. So I want to start with some initial spot checks that I like to do when I get a new data set in my lab. So the first things to check after loading in new data for me is more or less this list. Did the last rows or columns from the original file make it in? So often what I'll do is look at tail or play around with select and names in order to deal with and check whether or not I get the things that are all the way at the end, all the way at the bottom. It's very rarely the case that the things at the end or the bottom are correct, but stuff in the middle is incorrect. Note you may need to use a different package or manually specify the range with which you're going to load in the data. I'm trying to think. I had a data set that was like this recently. It was the historical info group business data, and I couldn't get to the bottom of the data set, so I had to specify that the reader skip the first, I don't know, 100,000 rows and only grab the ones after that so that I could verify that they were coming in correctly. Next, I'll ask, are the column names in good shape? Do I need to modify using the call names argument with that paste example that I had before with all the little I's and capital D's and what have you? Or do I need to just use the rename function and name a bunch of things that have weird spaces or characters that R doesn't like? Next, are there decorative or blank rows or columns to remove? This normally comes to you during like an Excel spreadsheet where somebody has skipped the first 6 rows because it's easier for a human reader. But since I'm making the computer read it, we don't need those. This often can just be dealt with filter and select. How are missing values represented? Are they NAs? Are they just spaces? Are they a period? Are they the number 99? I seem to recall there's a demography paper where people were trying to look at the amount of times that people were getting it on and how happy they were with their lives. And there was these people that were not very happy at all or were getting it on virtually all the time. And this was because they had loaded that it was 99s, meaning nothing, like they weren't getting it on, but they coded it like they were getting it on all the time. Don't be that person.
What data set is that?
What data set is that?
Yeah, what research?
I feel like that was probably important research for somebody. Oh. For these situations, you're going to want to use mutate with if-else statements to fix. Perhaps use in mass, you might want to use looping, or mutate across where is dot, that kind of thing. Also, are there character data, things like zip codes with leading zeros, being correctly represented as numeric or vice versa? I seem to recall in the flights data, there were a lot of times that had leading zeros, and if you manipulated them, those leading zeros would go away because it was on 24-hour time and was midnight 30. Modify the call types argument or use mutate as dot numeric. These kinds of things will help alleviate those problems. That's kind of the gist of spot checks for me. Other things that I normally tend to do at the beginning of opening a data set are normally quality of life things instead of spot check things. So let's get to talking about what it means to have tidy data. Here we have some slightly messy data that was collected back when Rebecca Farrell taught this class many years ago. So here we have data that looks great if you're a human person and reading to understand what the information is telling you, right? We have a program, the Evans School. There are 10 women and 6 men. Arts and sciences, 5 women, 6 men, and so on. This is messy data. And the reason that it's messy is that one of the columns has become 2 columns. This woman and man is its own column that should be called gender. And all of these things should be a count. And let me explain why, but first, we'll get there. So what is an observation here? A group of students from a program of a given gender is one observation. The variables here, one is program and the other is gender. And often you'll find that there are variables that are in your data set that are not specified, but are important for you to start like putting on your Sherlock Holmes hat and finding. So what are the values? We have the program, and then we have gender, which is woman or man, in the column headings, and it's not its own column. And now these data, which are essentially the same thing, are spread over 2 columns when they should just be 1. And so here I want to motivate the tidy version of this data set. each variable is now its own column, and each observation is now its own row. So for instance, if you wanted to throw this into a ggplot, it's ready to go. It'd be really easy to facet by different things. It'd be really easy to paint different layers with the different information. Whereas if you have this one, it would just be like pulling teeth. So let's return to our billboard data, which is like pretty ugly messy. It's not administrative data that's kept at the state local government, but it's close. So let's talk a little bit about what we have here. So we have the year, 2000, a good year. We have the artist, the track name, the time, which is written in minutes, then seconds, the date that it entered the Billboard charts, and then we have week 1 all the way through week 76. But one thing to note about this data set is that week 1 is relative to the week that it entered the Billboard Hot 100. So that means week 1 at rank 87, when Tupac's Baby Don't Cry entered the Billboard Hot 100, they're talking about the 4th week of February in this cell. But when Together's the hardest part of, I don't remember that song, I'm sorry. They entered in September. This is their rank at the 2nd week or the 1st week of September. So that means that the value here and the value here for week 1 are ranks at different times. And that's the case for 76 columns. So it becomes really difficult for me to tell, like, week 1 isn't the rank January 1st, even though that's probably how we want the data. It's a mess that we will tidy. Y'all remember the 18s? Hold on. The reason I say that, my neighbor, my downstairs neighbor, was just up Thursday night listening to like ABBA's Dancing Queen, just like back to back to back to back. I mean, Dancing Queen's good, but it's no voulez-vous. Okay, about the Billboard data. What are the observations in the data? We have the week since entering the Billboard Hot 100 per song. What are the variables in the data? We have the year and the artist and the track and the song length, the date it entered the Hot 100, and the week since first entered the Hot 100, which is spread over many columns. And then we also have the rank during that week, which is also spread over many columns. Now, what are the values in the data set? Note that these are not things that are necessarily described by the column names, and we'll need to make sense of them. So our values are stuff like 2000 is the year, the artist is 3 Doors Down, the track is Kryptonite, the song length is 3 minutes and 53 seconds, the date it entered is April 8th, 2000. And now in week 3, this is stuck in the column headings, this piece of information that's actually related to our observation level. And rank 68, which is spread over many different columns. So tidy data, also known as long data, are such that the values for a single observation, they're such that the values for a single observation are in their own row. The values for a single variable are in their own column. And there's only one value per cell. Now, by one value per cell, I don't necessarily mean that it only has, the length of the song. It can have multiple things inside of the cell, as long as that constitutes one value for you.
Like, what's in people? Hoping for one value.
Let's say that the column says years that the Atlanta Braves went to the World Series. And then it would be like 99 and now 2021.
So multiple things meaning two.
Right, like two pieces of information that constitute one value. But why would we want tidy data? I mean, I'm looking at that Evans School example and I'm thinking it's not so bad. Let me motivate you. First, it's easier to understand many rows rather than many columns as a reader. It's really difficult to recall as you read across left to right relative to thinking about observations that are all just duplicated over and over the same set of columns. Tidy data is required for plotting in ggplot2. And if you want to take advantage of those really excellent plot skills that you've developed, you want tidy data. It's also required for many types of statistical procedures, mixed effects models, hierarchical models, not SEM. But when you take SEM, you'll see why. Tidy data also makes for fewer confusing variable names. Right now, it's very confusing that we have week 1 through week 76, and that the contents of those columns don't mean the same thing over all of our rows. Also, there are fewer issues with missing values and imbalanced or repeated measures of the data. So lots of our columns right now in that Billboard data set are just like teeming with NAs because a song was only on the Hot 100 for 3 weeks. But there's now 76 columns full of NA, or 73 columns full of NAs for that particular track. So we use tidier. The package provides functions to tidy up data, similar to reshape in Stata or Varsto cases in SPSS. Some of its key functions are pivot longer. This takes a set of columns and pivots them down to make 2 new columns, which you can name yourself. A name column that stores the original column names, and a value column with values in those original columns. If I'm saying columns and names a lot right now, we'll get examples, it'll be okay. There's also the opposite of pivot longer, which is pivot wider. This inverts pivot longer by taking 2 columns and pivoting them up to make multiple columns. A particularly useful thing, in my opinion, is separate. This pulls apart one column into multiple columns. This is very common to do after you use pivot longer, where values are embedded in column names. There's also extract numeric, which does a simple version of this for the common case of when you just want to grab the number part. I was just using extract numeric this morning because I had a bunch of data where people are asked how much they get paid an hour. And some people said, I get $22.50 an hour. And other people said, I get $22.50. And I don't want to keep that an hour part. I know what it's supposed to mean. So I just want the number. Note there's also extract, which is for pivoting a column into multiple sets of columns. I don't have a really excellent example of this because this Stack Overflow answer is perfect. Just go find that one. It's actually by Hadley Wickham, like main architect of Tidyverse, answering a regular Stack Overflow question someone had. So let's check out pivot longer on our Billboard Hot 100 dataset. So what we're going to do is get the week and the rank variables out of their current layout into 2 columns. This will create a big increase in rows and drop a bunch of columns. So we load the library tidier and library dplyr. Also something to note, R doesn't really care about semicolons. So you can just put those between things if you really want to, in a case like this, to separate them. I often use semicolons when I'm writing for loops. We'll get there. So let's say we assign to Billboard 2000 our data that we loaded in, and then we pivot longer. Starts with WK. So this takes a lot of the same arguments that select can and a lot of the same helper functions. So we're going to say all of the columns that start with WK start with week. And then we're going to create a column names to week. And then the values from our WK columns, we're going to call rank. And note that the dimensions of our billboard data are now 24,000 rows and just 7 columns. We could instead use pivot longer, week 1 through week 76, like this. I tend to prefer this kind of format, but to each their own. This is just to pull contiguous columns. And now when we look at the pivoted weeks, this is what our data looks like. Each row is now a song week rather than just a song. And our week column tells us what week it is for that song being on the Hot 100. And our rank column tells us what rank it was during that week for that song. So we've taken all of those 76 rows and turned them, or 76 columns, and turned them into 2 columns full of information in the rows. How can we pivot better? So if we take a summary of our rank column from the Billboard 2000 dataset, we'll notice that it has 18,785 NAs. Remember all of those ones that are like after the song has fallen off of the Billboard charts. We don't want to keep those 18,785 rows with missing ranks, i.e. observations for weeks since entering the Hot 100 that the song was no longer on the Hot 100. So one way we could do this is we can actually supply an argument to pivot longer. The argument values drop NA equals true to pivot longer will remove rows with missing ranks. You could also, instead of doing this, just say filter is not is.na rank. These are equivalent expressions. Note that when we run this summary here, there's no more NAs over here. We've gotten rid of them. And now there are but 5,307 rows and 7 columns. The week column, regrettably, is a character, but it should be numeric. Tidier provides a convenience function to grab just the numeric information from a column that mixes text and numbers. So we could supply to our Billboard 2000 object the Billboard 2000 data, and then mutate week equals parse number week. And now when we run summary on week, we will get the numeric weeks that are in our data set rather than some characters. For more sophisticated conversion or pattern checking, you'll need to use string parsing, which we will be getting to in week 8 of this course. Okay, do we have any questions so far? Getting things tidied up. Tight. Yeah, or rather than try to parse out the WK, you can use the names prefix argument to pivot longer and supply to it after we drop the NAs, names prefix equals WK, and then names transform, and then we can supply to it like we did with across week equals as dot integer, and it will convert our week column into an integer already. I tend not to pivot longer and include these kinds of things because it's confusing to my brain. It's kind of a lot for me to look at and remember what it's doing. So I tend to kind of stop at this step and then use this kind of format. But I wanted to make sure that y'all were exposed to this way, where some people have lots of the options just put out. So it's only one command. But I'm no computer scientist. I'm not trying to optimize the amount of lines that I write in my R scripts. But now, when we look at our billboard data, we have our track week level observation. The week is an integer. Our rank is an integer. Things are looking good. An example for separate, the track length column is not analytically friendly. Let's convert it to a number rather than a character that's in minutes, seconds format. So we will take our billboard data and then separate our time column into two columns, which we will name minutes and seconds. And I want you to separate that column based on the colon. And then convert equals true. We'll convert the data type to the one that it seems like it is. So it'll make a guess based on, so right now we have a character data and we've separated the character data into two numbers. Convert equals true will guess that it is numbers and convert it to numbers. We can then mutate, make a new column called length, which is equal to minutes plus seconds divided by 60, so that we can put everything in decimal minutes. And then we'll get rid of our minutes and seconds columns. We don't really need those. And we run a summary on length, and we'll see that the shortest song was 2.6 minutes, and the longest one was 7.833 minutes. The sep argument here tells separate to split the column into two, where it finds a colon. Yep, said all that. So we don't necessarily use pivot wider all that often. It's not a ton of times it's the case that I have a data set that's too long and I need to make it wider, because it's the opposite of pivot longer, and longer normally means we're making something more tidy. But here's an example of when you might want to use this. When you have data for the same observation that's taking up multiple rows. So this is an example of data that we might want to pivot longer, unless we wanted to plot each statistic as its own facet for some reason. And so here we have our statistic column, which has the mean, the median, and the standard deviation. And now that makes our value column a little bit nonsensical, because we can't really compare like our 0.72 to our 1 because they're telling me different kinds of information. A common cue to use pivot wider is having measurements of different quantities in the same column. So let's say we want to make our too long data. I'll use the data.frame argument to replicate that same column that was in the last slide, or the same data frame that was in the last slide. And then we pivot wider the names from our statistic column and the values from our value column. And what we'll get is an observation per group. So it has taken all of these A's and collapsed them to one row, and then made a new column out of each of these statistics and supplied to that column the values from this column. I know, I don't pivot wider very often. So let's look at some charts of the 2000 data, but we're gonna need to do a little prep. Let's look at songs that hit the number 1 at some point and look how they got there versus songs that did not. So we'll group by artist and track, and then mutate weeks at number 1 is equal to the sum of the rank column that equals the number 1. This will provide us with the amount of rows that something was at 1, and peak rank equals if there was ever a time that this artist or track had the rank equals 1, return hit number 1 if true, didn't hit number 1 if false. And then we're going to ungroup. This allows for later analysis is not going to be based on these groups. Sometimes when you use group by, you're immediately going to put it in a plot, and so it's not a big deal that your data is grouped. But other times you want to do something to the data after that doesn't require these groups, you will want to call ungroup. Things to note. Any min rank equals 1 checks if any value of rank is equal to 1 for the given artist and track. That's what's going on there. And that's like per group. It's very strong when you use it in conjunction with group by. And I motivated what ungroup does. So here I've made a chart for the 2000 data. It's not especially complicated. I'd say that the only things of interest that aren't just making it look slightly nicer are here, the Y scale has been flipped upside down so that rank number 1 is at the top instead of the bottom, as we are used to making graphs where 0 and 1 are close to the bottom and high numbers are close to the top. And also the x-axis is logged, but we'll see it in a second. So here what we have is the peak rank of each song. If they ever hit number 1, they are highlighted in red. If they did not, they are not. Note there appears to be censoring around week 20 for songs falling out of the top 50. I will need to follow up on that, but this speaks to the virtue of graphing things frequently so that you know what's going on in all of your data rather than some of it. We can ask the question, which were the number 1 most weeks? And so we'll say, we'll take the Billboard data and then distinct by artist, track, and weeks at number 1, and then arrange in descending order of weeks at number 1. And here's the first 7 rows. Shout outs to Destiny's Child and Santana. Okay, we're moving on to dates and times. Do we have any other questions about tidying stuff up before we move on? Cool. About getting usable dates. We have the date the songs first charted, but not the dates for later weeks. We can calculate these now that the data are tidy. So let's say we take the Billboard data and then mutate date equals date.entered plus the week column -1 times 7. week com minus 1 times 7. Yes, so what's going on here is that things that are dates, we can actually increment using numbers. So here we've taken the date it entered and then subtracted the week and multiplied it by 7. And we will get the correct amount of incremented weeks for the track. We can take the Billboard data and then arrange by artist, track, week, and then select these columns so that we can see how well our data did. Note that it just used days for these kinds of calculations. We'll talk about in a second how to not make it do that. Yeah, this works because date objects are in the units of days. We can just add 7 days per week to the start date. So let's say we're preparing to plot over calendar time. We plot by day. None of these things are terribly interesting, with the exception of trying to describe the date often means that you'll have to use these ugly date descriptor things. I don't know what the name of them off the top of my head is right now, but they're in your help viewer in Lubridate and things. And here we can see all of the ranks per song over time, and it's just this big, old, messy hair thing. And this tells us how far back the data is willing to go to check if something was on the Hot 100 in the year 2000. And it included it all. So the data is not just including the year 2000, January 1st to December 31st. To practice working with finer grained temporal information, let's look at 1 day of SPD response data obtained by data.seattle.gov. Note, it still gives us our column specification with things of interest like, goodness, it gives us the longitude and latitude of exact police stops or police responses. It tells us things like the what cleared the event, why it was cleared, and lots of other, I don't know, top data. We can use the function glimpse on the SPD data. Glimpse is like structure, but better in most ways. And how it presents the data to you is a lot cleaner and easier to read. And I also like the way that it provides the first few rows in a more legible fashion. Highly recommend glimpse over structure. So let's look at this data using Lubridate. So let's look at the structure of just the event clearance date. We'll notice that it is in month, day, year, hour, minutes, seconds, time of day. We want this to be in date time format, which is called POSIX. It's not a character, or we don't want it to be a character data. We are going to be working with these dates using the Lubridate package. So library Lubridate, we make the SPD data, and we're going to mutate our event clearance date using MDY_HMS, which stands for month, day, year, hours, minutes, seconds. And we supply it this column, event clearance date, and the time zone, America, Los Angeles. The Lubridate package has things that can parse times for different setups of how time are written. So you can give it just weeks, or just the month, year, or just the minute, seconds. and so on. Now, when we look at the structure of this column, we'll notice that it is in POSIX CT character type, and that the format has changed to be the way that time works. Notice that it's now in the descending speed of time units instead of the colloquial setup, which is years move the slowest, then months move the slowest, then days move the, and so on. Also, a thing about converting things to POSIX time, it is aware of leap years and that kind of thing, whereas the earlier way that I was manipulating the weeks was not. So it's generally useful to convert things to dates to take care of things like February having 28 days. An aside on time. So time data are a bit weird. R uses two primary formats for storing time data on times and dates. There's POSIX CT, which is the one you're basically always going to see. This is a numeric vector of seconds that begins with 1970. And if you have a time that's prior to 1970, it'll be negative. It counts backwards on the timeline from 1970 for strange computer reasons that is related to Y2K fears and all of that. There's also POSIX LT, which is a named list of vectors containing lots of date time information. You'll very, very, very rarely run into POSIX LT. LibreDate gives us many convenience functions for dealing with date time data. It is often easiest to convert time to standard numeric values and work with it that way. However, particularly if it will be used as a variable in a statistical model. A few useful date time functions. So let's say that we want to get just a particular set of date times. We can say as.date, our first couple of rows in our event clearance data. We can then say weekdays, our first couple of rows, and what we'll get are just the days of the week. It knows. I find that to be so cool. I'm sure it's not cool for the computer. It's like every day, but I think it's really neat. You can also do things like add the duration 1 hour, and it will increment up, and it obeys time. It knows that after 11:58, if you add an hour, it's time for the next day. Very exciting. So let's ask the question, what time of day were incidents cleared? So we'll make this SPD times data frame by taking the SPD data and then selecting just the initial type group, which is the thing for which the police were called, and the event clearance date. And then we'll mutate the hour that it occurred and create a plot, facet wrapping by the reason for the response. And so here we can have the SPD event clearances for March 25th of 2016. And it's faceted by all of the events for which they were called. So things like animal complaints, auto recoveries, parks exclusions, etc. One thing about looking at this facet is that, I don't know, it's kind of all over the place. It's in alphabetical order, and I don't know what all of the reasons that the police would they themselves self-report the reason that they were going to a thing for is. Which brings us to the next thing, managing factor variables. So factors are such a common and fussy vector type in R that we need to get to know them a little bit better when preparing data sets. The order of factor levels controls the order of categories in tables, on axes, in legends, and in facets in ggplot2. Often we want to plot in interpretable and aesthetically pleasing order, things like from highest to lowest values, not Alabama first. If you're in my line of work, Alabama's on the first thing on plots a lot. And it's just, I don't know. Alabama's like fine, but top 7 southern states. The lowest level of a factor is treated as a reference for regression, and the other levels get their own coefficients. You'll often see this in papers. They'll say our reference category was, you know, a ethnic group of some kind, this placebo, et cetera, et cetera. Reference levels are by default alphabetical, which doesn't necessarily coincide with the easiest to understand baseline category, which again happens in my field a lot, where the reference category is for some reason Alabama. And for this, we have 4 cats. Regrettably, 4 cats is an anagram of factor and also means 4 categoricals. And if you feel like nerds shouldn't name things before. So the tidyverse family of packages includes the package 4cats. This package supersedes the functionality of the base factor functions with a somewhat more logical and uniform syntax. There's a really in-depth 4cats manual by the legendary Jenny Bryan. So let's say we want to convert this character to a factor. So we have this initial type group column with things like theft and trespassing and crisis call. If we want to mutate it, change it to be something else like a factor, we could say SPD times and then mutate initial type group equals factor initial type group. What we'll see is that now there are 30 levels and that they are in fact in alphabetical order. And that this is mostly nonsensical to us. If we look at them as a numeric, we can find their underlying numeric values. So theft is 25, trespassing is 28, crisis call is 6. And that these are probably not how we want to deal with these data. So let's relevel it by, say, the frequency. We can use the function factor in frequency, which reorders the factor levels by the frequency they appear in the data. So here, we take the SPD times data and then mutate initial type group equals FCT in frec. And now when we look at the first 4 rows of the levels, we'll see that suspicious circumstances is number 1, and traffic related calls is number 2, and theft is number 3. And now the most common levels are first. So when we plot it again, using the same format for our plot from before, we get a plot that's way easier to look at and understand, despite having tons of data on the screen. I can immediately say that, I don't know, there are a few gun calls, but there were a lot of traffic related calls, and that those things seem to be related to the total surface area of our bar plots. There are other ways to reorder things. A general way to reorder a factor is through the factor reorder function, aptly named. So the way we set it up is to say factor reorder our factor vector. We had provided a quantity to order it by, and the function to apply to quantities by factor. Here's an example. This is especially useful for making legends go from highest to lowest value visually using the max as your function, or making axis labels that go from lowest to highest value using mean. You use the factory level factory level function and use. Okay, yes, you use factory level and the reference argument ref equals to change the reference category. And this is great when you want like a very specific change in, I don't know, how your logistic regression model is outputting something. An example of reordering, we'll use Jay-Z. Remember when Jay-Z's name was in all caps? Wow. So let's make the Jay-Z data frame, taking our Billboard data and then filter to the artist Jay-Z, and then mutate track equals factor track. And here's what we'll get when we plot the week by the rank, which is like fine, but the legend's not great. The legend is actually a little bit counterintuitive because it's in alphabetical order. And volume 2 was good, but I mean, anything wasn't, it's not my favorite Jay-Z song. So what we could do is use factor reorder to reorder the track column by the rank and the minimum rank that it was. And so now our legend has I Just Want to Love You at the top and Big Pimpin' second. And it matches what our data is telling us in the plot. Okay, do we have any questions there? Cool. About dropping unused levels. So after subsetting, you can end up with fewer realized levels than before in your factor. So there might just be some cases that don't have, or some levels that don't have any cases for them. But the old levels will remain linked and can cause problems for regressions. I know that a lot of you encountered this with the Gapminder data, as you would subset to, 10 countries, but it would say my country variable has 125 levels in it. You can drop unused levels from variables of your entire data frame using drop levels. So we could say Jay-Z's biggest, filter, track, %, I Just Want to Love You, and Big Pimpin'. And now our level still has all 5 of these songs, even though our data set only has 2 of the songs. And if we pipe this into drop levels, now our levels are just those 2 songs. Well, this maybe isn't terribly interesting when you're trying to, check out Jay-Z songs. When your regression estimates are accurate, you'll be excited. For the homework, this is our first of the 2-part homeworks. I'm going to say this now. I think this is the hard one. I don't feel like we've had any hard ones yet. And for that, I'm sorry. So what it is vote tallies in King County from the 2016 general election. They're in a 60 megabit comma delimited text file that's downloaded from King County, and they can be found on the course website. Take the one from the course website and not the one from the King County. The King County one has been slightly massaged so that this homework isn't extra hard. The data have no documentation aside from what I provide. So show your detective work to answer questions about the data and clean them up in an R Markdown template that's also on the course website. Be sure to use the Apple curly Q click thing on Mac or right click on Windows to download the .rmd file to the folder that you plan to work from, then open it in RStudio. I actually think I was supposed to change the slide. I'm pretty sure if you go to the course website and click on the template, it will just open up the raw version of it, and then you can just copy paste it from there instead of downloading it. I was having some issues with that. If you can still download it, then that might have just been because I was on one of these computers. You know how it gets upset about checking for viruses. Anyways, the homework is in 2 parts to be completed in each of the next 2 weeks. It can be daunting, so do not wait until Monday to start. I recommend reading instructions closely, working with others, using the mailing list and the Slack. The part 1 is due next week, and the part 2 is due in 2 weeks. I will be going through part 1 step by step in lab on Monday. I don't know. Good luck. That's going on. I see. This is, you just had to refresh.